Hello everyone, and welcome back to MP Coding. In this video, I'm going to teach you how to correctly render the LVGL UI to the STM32F MCU with a TFT display. At the end of the video, I will show you how to set this UI onto the TFT display. Let's start. For this example, I am using the STM32F429 Discovery board. It comes with onboard 64 megabit SDRAM and a 240 by 320 TFT display. The display is driven using the STM32F429 driver. The display MCU is configured as a 4-wire 8-bit serial SPI connection. This SPI is used only to configure the STM32F429 registers. The parallel 16-bit RGB interface is used to continuously push the pixel data to the LCD. I will explain those details inside the video. Now, let's start. Open STM32Cube IDE and create a new STM32 project. Select the STM32F429 iDisco board from the board selector. Name your project and click Finish. When prompted to initialize the board with default settings, click Yes. But don't worry, I'll walk you through the specific configurations we need for this project. You'll notice that most of the required MCU pins are already configured based on the default board setup. If you'd like to verify the pin layout, you can open the board schematic for reference. Let's disable the components we won't be using. In middleware, disable ROTs, we won't need it for this demo. Disable USB host as well. Under Computing, uncheck CRC. LVGL can work without it. Under Connectivity, disable USB OTG/HS and use ART1. Now let's review the components we do need. FMC connects to the external SDRAM. If you're not familiar with how to set up SDRAM, I've created a separate video covering that, from pin configuration to memory testing. You'll find the link in the description. I2C3, this is used for the touch input. On the board, I2C3 connects to the STM32F429 touch controller. The STM32F429's touch pins, YD, YU, XL, XR, are internally connected to the display MCU. SPI5, this is used to send initialization commands to the STM32F429 display controller. Under System Core, set the time-based source to system tick. Under Timers, disable Timer 1, we won't be using it. Go to the Multimedia section and LTDC. The LTDC peripheral uses a 16-bit RGB 565 parallel interface to send pixel data to the display. That's the mode we will stick with. The MCU's DB0 to DB17 pins are connected directly to the display's RGB input. The default GPIO configuration already sets this up, so we don't need to assign pins manually. If you're building a custom board, you'll need to map these pins yourself based on your display's datasheet. This is how it configured display MCU. I'll upload this reference sheet to the GitHub. You can read that also. You can use 2 layers if you want, but I will use only 1 layer, and the layer color format is also selected as RGB 565. Then, the color frame buffer start address is very important. The default address is 0xD followed by 7 zeros. That is the SDRAM Bank 2 start address. If we look at the reference manual of the STM32F4 MCU, under the FMC section for external device address mapping, you will see the SDRAM Bank 2 starting address, which is the same as the LTDC frame buffer start address. So, we are going to use SDRAM to store pixel data for LTDC. Next is the DMA2D settings. DMA2D, also known as the Chrom-ART accelerator, is a specialized direct memory access engine designed for image manipulation in embedded systems, particularly for microcontrollers. I will explain how to use this with code. For more information, I have written a Medium article about DMA2D, which you can also read. I will leave the link in the description. Now, all the pins are configured, but you can always check the board schematic and compare the pin functions and connections. LED1 and LED2 connected to these pins. I will leave those as our output GPIO pins. Next, go to clock configuration and set up the clock. I am going to set the high-speed clock to the maximum 180 MHz. To do that, configure the following settings. Next, for the LCD TFT clock, I will set it to 6 MHz with these settings. Now generate the code. To test the generated code, let's toggle the onboard LEDs. The onboard LEDs are connected to GPIO pins 13 and 14. Let's build the project. You will see there are no errors. Now let's debug it. You should now see the LEDs toggling on the board. Okay, let's start setting up the LCD. This LCD uses the ILI9341 driver, so we need the driver implementation. You can download it from GitHub. But if we look at the STM32Cube repository, inside the drivers, BSP, components folder of the STM32F4 firmware, you can find a folder for the ILI9341. Inside this folder, we can find the driver files. Let's copy these into our project. Create a new BSP folder inside the drivers folder. Add a new components folder and an ILI9341 folder as well. Then copy those files into the ILI9341 folder. Open the header file. Comment out the include directive. We're not going to use the LCD driver structure this time, so the definitions inside that included header are not needed. Also, comment out the extern variable. Next, open the driver source file and comment out the interface structure. Then save the files. We need to implement the LCD I/O functions. All other LCD drivers follow a similar structure. In every case, we need to implement these I/O functions to set up the driver with our configuration. The same method applies to the touch driver. I'll show that too during the touch initialization. To implement these functions, let's create a .h and .c file called lcd_config. Include header file also. Okay, let's copy and paste the I/O function declarations into the header file. Then, in the .c file, let's implement them. To implement these, I'll use the default implementation from the Discovery Board's firmware folder. Open the STM32 Cube firmware folder for the STM32F429 Discovery. You can see the STM32F429 Discovery.c file. Open the file. Here we can see the implementation of those functions. Let's look at them one by one. First, the LCD-IO init function. You can see that some GPIO pins are set up, and the CS pin is reset. Also, the SPI initialization is done here. If we check the LCD MCU datasheet, we can find out what these pins are used for. The CS pin is for chip select of the SPI. You can check each one to understand better. I'm not going to explain them one by one here. If we go to the main.c file and look at the GPIO initialization, we can see these pins are already initialized. These are auto-generated when we generate the project. So there's no need to set them up again. But we can reset the SPI line to select the chip. Let's just reset the CS pin only. Include main.h file here. Before that, let me quickly open this project in VS Code. It's easier to use than STM32 Cube IDE. Next, define the CS pin set and reset macros. The CS pin is connected to GPIO-C, pin 2. If we look at the GPIO initialization in main.c, we can see the CS pin is named CSX_pin. Let's use that, it's cleaner this way. Now let's implement the LCD-IO init function. Inside this function, just reset the CS pin. Next is the LCD-IO write data function. If we look again at the driver function, we can see the implementation. Let's copy that and paste it into our implementation. Here, we can see the WRX pin is set to high. If we open the schematic, we can see that the WRX pin is connected to PD13. In the main.c GPIO initialization, the WRX pin is named WRX_DCX_pin, and its GPIO pin 13. Let's define the WRX macros as well. Next, we need to implement the SPI write function. If we look at the firmware file, we can find that the function simply transmits 8-bit data over SPI. Let's copy this function into our code. We need to provide the SPI handler, in this case, SPI5. We'll get that SPI handler from the main.c file using the extern keyword. The max timeout for SPI can also be copied from the firmware function. Change the SPI error handler to the normal error handler. I'm not going to set up any custom error handlers, but you can add one if you like. In the same way, let's copy and paste the other LCD-IO implementations as well. They are very easy to understand, just simple SPI read and write methods. In this case, we won't be using the SPI read method, but I'll copy that too. I forgot to mention one thing. Open the ILI9341.h header file and add the stdint.h standard library include to fix the init declarations. That's all you need to do to set up the ILI9341 driver for the LCD. Now open the main.c file and call the initialization function for the ILI9341 driver. Also, include its header file. Before building the project to check for any errors, add the BSP folder to the include directories. Open the project properties. Under GCC compiler, include paths, add the BSP folder. Build a project. You'll see it builds successfully, but with some warnings. These warnings are because I forgot to change the error handler function in the SPI code. Let's quickly fix that. Build again. This time, there are no warnings. Before starting to render anything to the LCD, we have some other setup related to SDRAM. In my last video, I showed how to correctly configure the SDRAM. I'm not going into detail here. Just copy the code from my Medium article. You can either watch my last video or read the Medium post related to this. I will add the link in the description. I will paste that code here, and then call the function after FMC initialization. Don't forget to add the function declaration as well. These settings are very important to set up the SDRAM. Please watch my other video to get the idea. First, let's fill the color to the display using DMA2D, with the register-to-memory method. In the auto-generated DMA2D initialization, it's set to memory transfer with foreground and background layers. But I'll use just register-to-memory, no need for layer configuration. For a detailed understanding of DMA2D, you can read my Medium article. Let's create a new function to fill the LCD with one color. In this function, we need to initialize DMA2D, and then write the color into the memory buffer. We can find a similar fill buffer function in the Discovery Board firmware files. Open that file for reference. First, initialize the DMA2D. Then fill the buffer. And finally, poll the DMA transfer. Copy the mode settings from that code also. Now give the DMA2D handler name according to our code. Set the output offset to 0, we're not going to use any offset. Let's get the color value from a function parameter. Inhale DMA2D init, pass the DMA2D handler, and if initialization fails, call the error handler. Next is the HAL DMA2D start function, which writes the color value to the LCD. Because we selected register to memory mode, there's no source buffer, just a color value. The destination address is the SDRAM start address, the same one we set for the LTDC color frame buffer start address. The last parameters are the width and height of the fill area. We're going to fill the full screen, so give the full screen width and height. Add function declaration also. Another thing to mention, we set the color mode to ARGB 8888 format here, with register to memory mode. But the LTDC pixel format wasn't changed to ARGB 8888. So we should use the same color mode for both LTDC and DMA 2D, since we're not using any layer blending or color conversion. I explained this in more detail in my Medium article, please read that for more information. In the fill buffer function, we need to pass the color value in 32-bit ARGB 8888 format. In the main loop, let's pass red, green, and blue color values with a 1-second delay, so we can test if it works. Don't forget to comment out the auto-generated DMA 2D initialization, we don't need that anymore. Build the project, there are no errors. Let's debug the code. You should now see the colors displayed on the LCD. Next, let's start setting up LVGL. First, we need to download or clone the LVGL repository from GitHub. But we need to consider which version we're going to use. In the end, what we want is to run the Smart Gadget example project on our screen, and that example supports LVGL version 8.3.11. Also with 16-bit color depth. So we need to clone that specific release. You can go ahead and clone the repository. I have already cloned the repository, so I will copy the LVGL folder into our project's BSB folder. If I open the lvgl.h file, you can see the LVGL version is 8.3.11, exactly the version we need. Let's start configuring LVGL. To configure the settings, we need to copy the template.h file 1 folder up. Then set this to 1 to enable the content. Next, set STM32 DMA 2D to 1. Also include the STM32 MCU header. Since we are using STM32F4, let's define that header. Then save the file. Make sure to rename the file to lv_conf.h. This time, let's use direct memory access. You can also use DMA 2D the same way. DMA is easier to use because we don't need to worry about layer blending or color inputs. LVGL generates all the required data, we just need to pass LVGL's color buffer directly to the LTDC frame buffer. Let's start. Open the LCD config file and create a new function to initialize the LVGL flush. In this function, we'll first initialize DMA. I have already created this initialization function, so I'll copy and paste it here. Also, the related callback functions. We need a DMA handler. Let's add that. First, the DMA init function does the basic setup of the DMA controller. It enables the clock for DMA2. Then it configures the DMA to do memory-to-memory transfers, which means it can copy data from one RAM area to another. It enables 16-bit data alignment, which matches the LTDC RGB 565 format. It enables the FIFO buffer, sets it to 1/4 full threshold, and configures the DMA priority as high. Then it initializes DMA2 stream 0, which we'll use for these transfers. Finally, it registers callback functions that get called when the DMA transfer is complete or if there's an error. Let's add these variables. These are handle the draw area. Include the LVGL header file. This is the LTDC starting address, defined using a 16-bit pointer. This address is the start of external SDRAM bank 2, and it's also the start address used by the LTDC color frame buffer. So whatever we copy here using DMA or DMA2D will be displayed on the screen by the LTDC peripheral. At this display driver structure, it's need to be registered by HAL. And color depth pointer from LVGL. This is the display width. Let's quickly define that. Also define the height of the display. This function is called automatically when one line of the image is copied using DMA. We are not copying the full image at once. Instead, we copy one horizontal line at a time, and for each line, this callback is called. The variable y_fill_act keeps track of the current line being transferred. This tells LVGL, the flush is done, you can continue rendering the next part of the screen. If we're not done yet, we move the buffer pointer forward by one line. And we start another DMA transfer for the next line. This method ensures non-blocking rendering, and lets us use DMA interrupts to handle the copy operation line by line in the background, which saves CPU time. We enabled the DMA2 stream 0 interrupt. Let's add a function to handle the DMA stream interrupt request. We enabled the DMA2 stream 0 interrupt. Let's add a function to handle the DMA stream interrupt request. Then we call DMA IRQ handler, which will internally call the correct callback DMA transfer complete or DMA transfer error that we registered earlier. Call the DMA init function inside your LVGL flush init function. Next, we need to define LVGL frame buffers. Let me copy those as well. These two buffers, disp_buff1, disp_buff2, are used by LVGL for double buffering. Each buffer can hold 60 lines of pixels. While one buffer is being flushed, the next one is used for drawing, which avoids flickering. We pass them to display draw buffer init to initialize LVGL's drawing buffer. Display width multiply by 40 tells LVGL to use 40 lines per flush, which is a balance between memory usage and performance. You can increase up to 60 lines what we select for each buffer. If we add more lines, make sure to not exclude the memory. This initializes the display driver structure with default values. We'll assign our buffer, resolution, and flush function to this driver next. Draw_buff assigns the drawing buffer we set up earlier. Flush_CB, LVGL calls this when it's time to draw something on the screen. Monitor_CB, optional callback to monitor rendering performance. Horizontal and vertical resolution, set your screen resolution. Lastly, registers this display driver so LVGL can start using it. Next, the important one, flush method. In this function, validates the flush area to ensure it's inside the screen boundaries. Stores the current area and buffer pointer. Starts a DMA transfer of one row of pixels. The rest of the transfer is handled line by line in DMA transfer complete. These are all the steps needed to set up LVGL. One thing to check. In the LVGL configuration file, we set the color depth to 16-bit RGB 565. Let's make sure the LTDC pixel format is also set to RGB 565. Previously we changed it to RGB 8888 for a DMA2D test, so now switch it back to RGB 565. Let's initialize LVGL in main.c. First call lvinit, then call your flush initialization. Make sure to add the flush init function declaration in the header file. Include the lcd_conf.h file in main.c. Also, to test LVGL, include the lv_examples.h. Now you can initialize any LVGL examples here. But I'm going to initialize the demo widgets instead. If you look at the demo widget initialization function, it might not be enabled by default. Go to the lv_conf.h file and enable the demo widgets. I'm not going to use the slideshow. If you want it, enable that too. In the while loop, remove the fill color functions. Now add a delay and the LVGL task handler inside the while loop. Just using HAL delay won't increment the LVGL tick. You need to add a tick in the system tick_handler. Go to the default interrupt service file and find system tick_handler. Add these lines. LV_tick_inc1 tells LVGL that one tick has passed. LVGL uses this internal tick to manage animations, screen refresh, and timeouts. Don't forget to include the LVGL header file in this file. That's all we need to set up LVGL. Let's build the project. The build completed successfully, with some minor warnings. Let's debug the code. Now you can see the LVGL demo widgets rendered correctly. We haven't initialized the touch input yet, so touch won't work. But if you enable the slideshow in the demo, you will see the screens moving automatically. Let's start setting up the touch input. The touch controller is connected using I2C. When we generated the project, the auto-generated code already initialized the I2C peripheral. What we selected from the STM32 MCU setup. An I2C3 is connected to the STM32F429. Now what we need to do is implement the STM32F429 driver I/O functions. We can download this driver from GitHub. But same as the other drivers, we can find this driver also in the STM32F4 firmware folder. It's located in the same place as the ILI9341 driver along with other drivers. Inside the Components folder, create a new folder named STM32F429. Copy both the source and header files into our newly created STM32F429 folder. Open the header file. Comment out the include directives. We don't want the BSP interface in this driver. Include the standard library stdint.h. Scroll down and comment out the extern variables as well, we won't use them. Also, in one function's parameter list, there's a type defined as an enum. We're not using that function, so just change the type to uint8_t instead of the enum definition. Save the file and open the source file. First, comment out the structure definitions at the top, we are not using them either. Then scroll down to the function with the updated parameter type. Simply comment out its implementations and change the input parameter type as required. We won't going to use these functions. Those are the main things that need to be changed in the STM32F429 driver files. Now if we look in the header file, we can see a list of I/O functions that we need to implement. These are similar to what we did in the ILI9341 library. We just need to implement how the driver communicates, in this case, using I2C. Copy the I/O function declarations and paste them into our LCD config header file. Let's start with the first one, IOE_init. If we look at the Discovery board firmware file, we can find the same implementation. For IOE_init, the function simply initializes the I2C. Actually, if we check our main.c, I2C3 initialization is already generated by STM32Cube IDE, so we don't need to reinitialize it. So IOE_init is empty. If you want cleaner code, you could move the initialization from main.c into IOE_init. But I'll leave it as it is. Now let's quickly implement the other IOE functions. You can follow the firmware example or just follow along with this video. In most cases, when using an external device driver, you just need to implement how the chip reads and writes with master MCU peripherals. You can follow what I do here or copy the implementation from the firmware folder. So I'll speed up this part. Next, we need to set up touch input to LVGL. Create a new function called touchpad init. First we need to initialize the STM32F429. For that we need call this function with the I2C address. This comes from the 7-bit I2C address. We can check it in schematic. This 7-bit address with a 0 for write mode becomes 8-bit value. And it's 82 in hex. Let's define this address. Pass that address to this init function. Next we need to start transmit. Then we initialize the LVGL input driver. We need to set up touch input callback function. And next set the input method. So this case touch input. Finally, register the input driver. Now let's implement the touch callback function. I have already created these functions. So I copy and paste. These functions read the current touch state. If the screen is touched, they set the touch point coordinates and mark the state as pressed. If not, they retain the last coordinates and set the state as released. LVGL uses this data to detect touch input and track touch coordinates. You can check the implementation in my GitHub repository to better understand how it works. That's the complete setup for touch input using STM32F429 with I2C in LVGL. Let's build the project to check for errors. Okay, there are no errors. Let's debug the code and check whether the touch input is working or not. You can see the touch input is working. Okay, now let's create a new UI using SquareLine Studio. Open SquareLine Studio and create this smart gadget example for a 240 by 320 display with 16-bit color depth. Make sure the LVGL version matches your project's LVGL version that I mentioned earlier. I'm going to delete these image components. These images are large files for our SDRAM. You could select smaller images instead, but for this example I'll just delete these two image components. Let's run this and see how it looks. Now, let's export the UI files. First, go to Project Settings. And check the LVGL version. Color depth is set to 16-bit, to match our LVGL configuration. No other settings need to be modified for this example. Finally, specify the export destination folder. Apply the changes, then go and export the UI files. Check the export location. You will see the generated UI files there. Next, we need to copy these into our project. Navigate to our BSP folder and create a new directory named UI. Then copy all the generated UI files into this new folder. Include the UI header file to main.c. Comment out the existing LVGL widgets example. Add the UI initialization. Let's build the project. There appears to be an error where the UI example is trying to use font Montserrat 18, but this font hasn't been defined in the project. Open LV config file and enable Montserrat 18. Save the file and build again. The project now builds successfully without errors. Let's download the code. The UI is now rendering correctly on the display. In this video, we covered everything you need to render an LVGL UI on the STM32F429 Discovery board, step by step, starting from setting up the CubeIDE project, configuring SDRAM, LTDC, and DMA, DMA2D, all the way to initializing LVGL, adding touch support using the STM32F429, and finally integrating a UI from SquareLine Studio. You now have a complete and working LVGL system with hardware-accelerated rendering and touch input on STM32. And that's how you create a custom UI for STM32 MCUs with LCD displays using LVGL. We used SquareLine Studio to design the UI, and then integrated it into the STM32 project step by step. Now, you can build any UI in SquareLine Studio and bring it to life on your microcontroller. All the project files, configurations, and resources I used will be available in the GitHub repo linked in the description. Thanks for watching, and see you in the next one.